Okay, hello. So today I will show you work on AS rankings. So I will give a little recall on inter-domain reachability handled by the BGP protocol. Then I will give some motivation about this study about AS rankings. And then I will present you the new approach to rank ASs. And finally, I will show an overview of the classification. Okay, there is a bug with that. Okay, thank you. Sorry about that. Okay, let's go. So the internet network is a set of interconnected autonomous systems. So we've got stub networks. I mean, it's like more than client ASs that only send and receive traffic for themselves. We also got internet service providers, so they provide transit for other ASs. And the internet network is also a partition of the public IP address space. So the range of addresses are called prefixes. So we've got prefixes for companies, users, universities, and so on. And so the routing from the AS to the prefixes is handled by the BGP protocol, as you all know it. So BGP routers are responsible to propagate announce for the reachability of prefixes. And the routers maintain huge routing table toward all the prefixes. So the internet connectivity can be defined by the fact that each router would know a route toward any public IP address for the routing to work. Okay, so the end-to-end routes in the internet rely on the BGP routes selected and propagated by routers. And the router path inside each AS is matter only of the IGP of those AS. But the BGP route selection and propagation rely on two important things. First, the topology. So the BGP routes that would be propagated and selected depends on the AS level map and also the router level topology. And this selection strongly rely on routing policies. So how prefixes are announced, how the filters are set in configurations, and how the preferences are also set. Okay, so that was a bit a recall. So that was a technical part, and now we all know that the internet is a huge business place. So we've got business agreements between ASs. We've got agreements between customer and provider. So the client pays for incoming and outgoing traffic to a provider, as the first scheme shows it. So in terms of BGP, the client will send its client routes, and the provider would have to send all its routes to the client. We've also got another agreement called peering relationship. That you all know it. I love peering t-shirts here. So peering, usually it's no money, and we can say no guarantee. The particularity of those agreements is that we haven't got any transits between peers. The peer relationship only support routing between clients of clients. So there are also other relations. I mean, regional peering, transit peering, IP prefix-based relationships to access some prefixes, and sibling relationships. Okay, so for the point of view of an ISP to decide for new links or to maintain some links, we would have to know the reachability of ASs. I mean, which BGP paths are used or will be used to prefixes. So those paths, they depend on many unknown factors. I mean, business agreements, traffic engineering concerns, and the network dynamics of BGP. And this reachability is so important because it implies the underlying quality for the data plane. Of course, we all know that. And so, given an AS, business agreements you've got with your neighbors and the path your neighbors got to prefixes, it shapes your possible path to all the internet. So to accurately negotiate new links or to maintain actual links, we would need knowledge about which prefixes and which rules will be provided. When I mean which prefixes, I mean will I have cheaper prefixes with this new peer? Or which hosts are belonging to prefixes? Am I close to Google, for example, or something like that? And what kind of BGP paths will I get toward those prefixes? I mean, are they stable or something like that? So all this kind of information is relatively unknown. And so the real impact of a new link is unknown. So negotiations are complex. Okay, so to motivate this work, so AS rankings is just a classification of ASs. It's a way to compare several ASs, I mean transit ISPs. So it's to get an overview of the hierarchical position, so it's the economic position in the internet, and an overview of the topological position, so which connectivity can I get with a neighbor AS. So so the reachability of those candidate AS is strongly correlated to the position in the hierarchy. So the customer-provider relationships, they shape how packets will flow. Oh, I've got an animation, but I think it doesn't work. So this network should be transformed into a pyramid. Okay. So an overview of past works about AS rankings. So the whole approach were based on what we can call BGP tomography. So the idea is to get public data, for example, from root views. So we've got so many BGP paths to prefixes from many vintage ASs. And with those data, with those paths, we try to estimate the position of an AS in this internet hierarchy. So to do that, we've got many work proposed. We've got what I call black boxes, because algorithms are not public. So we've got netconfigs rankings, fixed orbit, and Renesis that is well known. So usually they do not publish how they rank ESs. Maybe Renesis people can say the contrary. I don't know. So we've got also research works on the internet hierarchy. I mean, work from Geo, work from Subramanian. So there are many other works. So I just put the first work on it. So they try to infer the hierarchical position from those BGP tables. And we also got CADA rankings. So it is I heard it is a bit out of date, but I don't really know about it. So their main goal was to compute the size of customer cones. What we call customer cones is that the amount of prefixes behind an AS. I mean prefixes of their clients and clients of clients. So prefixes they provide, in fact. So the methodology was to infer AS-level connectivity of the internet, then to infer business agreements, and then with those business agreements, they can infer the size of the cone. Okay, so last approach, we can say that it's linear algebra approach. So it's purely graph-based approach. We've got a French approach, one from Clairaut. So they try to analyze the matrix of the AS connectivity. We've got a recent approach from Wang and al. So it's about the same idea of using the matrices of connections between ASs. So as I will show, there are many issues in the estimation of AS rankings, and many rankings are not accurate. First, what we can say is graph-based metrics, they are not taking care of policies, so they are out of scope. Because BGP paths, they will never be shortest paths. They are policy paths. We all know that. So, for example, betweenness centrality, number of triangles in the graph, clustering coefficients, and so on, they don't work. And so next, if we try to use BGP tomography, I mean BGP paths to prefixes, to estimate the reachability of all the ASs, it's not accurate, one more time, because we've got a small number of measurement ASs, and we've got a strong bias in the data. So we cannot say only with root views, RIPE data, and some looking glass data, we cannot infer all the paths from all the ASs. So because we do not see any prefix, we do not see enough prefixes. And if we merge all this data from the vintage ASs, we've got some indicators overestimated. I've got a concrete example, for example, Colt, the AS from Colt is the 8220, AS 8220. So we can see prefixes going from one tier 1 to Colt and going to another tier 1s. So if you merge all data and you don't take care of prefixes, you can see this AS making transit for tier 1s. And it does that for such few prefixes. But if you forget prefixes, that's what you can infer with, blind algorithm, blind graph algorithm. So, and finally, if we use inferred business relationship to infer customers, as SCADA do that, we are not fairly accurate because the problem of inferring business relationships is a degenerated problem. I mean, so many solutions exist to the inference problem. So SCADA algorithm can provide solutions, but so many solutions have the same cost regarding the optimization results. And the model of agreements is to course to identify the complex reality of agreements. So what we propose to mine this data to infer accurate rankings. So we still use the feeds from root views, from RIPE, from looking glass routers. We have about 100 ASs full routing tables. So our goal is to estimate the amount of customer prefix provided by each AS. So this is the same goal as SCADA. But we do not want to rely on business relationships. We do not want the bias in the data introduced by the small set of measurement points. And we would like to put a freedom on the way to give importance to prefixes. I mean, to weight prefixes based on content, for example. So we keep in mind this bias in the estimation of amount of prefix we can observe in the graph, in the whole internet. So we know we cannot infer accurately prefixes seen by ASs. And we cannot fairly accurately infer prefixes on links. So what we will try to do is to infer the amount of space behind an ASs. So, and because reachability has to be maintained by every AS, so transit provider will be responsible for the propagation of enants of reachability. So we will still see those enances from any vantage points, and the transit provider will be seen on the route to customer prefixes. So we are sure of that. We will always see that. So we propose two splits paths we observed. So I give an example, a path XWZT to a prefix from the vantage point X. So we infer that the AS, So the one AS transit for a prefix P, and the second AS Z also transit for the prefix P. So given a set of paths, we can compute a set of prefixes transited by ASs. So those prefixes transited are those seen on a subpath of length 3. I call them triplets. And the rank of an AS will be the average amount of prefixes of, space transited by ASs. So we split the set of input paths for each vantage point. For each vantage point, we compute the prefixes transited, and then we compute the average of this rank. Okay, so here is something for the understanding. So given the vantage point AS5, we've got here 4 paths, and from the path 5, 3, 2, 4, 6, we can infer 3 informations. So we can see that AS3 has transited the prefix, AS2 also, AS4 also. And from another path, 5, 3, 4, 7, we can infer that AS3 has transited the prefix, and AS4 also. And it's the same with the other vantage point, AS4. So we can infer AS3 has transited something, and AS5 also. So this is slightly different from the way it's not to estimate the BGP routing table of an AS. It's just to estimate how an AS has transited to its customer. And the idea to compute the average rank is like to put away the transit seen when we are close to the AS. Okay, so advantage of this ranking. Intuitively, any AS that is far from my vantage point, we will only see him transit to its customers. So what we extract from the data is the perfect information. But if we got a vantage AS close, if we got an AS close to a measurement AS, we can see him transit so many things. So this will be pushed out by the average thing. So we can say we strongly reduce the bias due to the placement of measurement points. And we still keep the prefix granularity. So the transit of some prefixes between 2 tier 1s will be pushed out too. So, and finally, to compute this average IP space transited by each AS is quite, we can say quite accurate given a sample of 100 ASs. So here is an overview of the results. So I do not compare these results to other rankings. I should do that, but it's just to get an overview of that. And just when I look at other rankings, I can see some ASs getting into this top 20, and they should not belong to this top 20. And in my rankings, I think they should all belong to this list. And what's funny, it's for the case of my company, Open Transit. If we look at the rankings of other rankings, we can be like 25, 30, things like that. And if we take a look at this ranking that should reduce the bias and reduce many things I explained, we are 13. So this benefits us also. Okay. So here is the second part of the list. And I'm sorry for the names of the ASs. I just get a data from some little data from Whois databases, and it's not quite accurate names. Okay, so to conclude with this work, we introduce a new algorithm. So it's still based on BGP tomography things. We use BGP feeds, and we need root views to do that. So we record foreign transit of prefixes by ASs. So the value computed can be directly interpreted. For example, if we take level 3, so from the point of view of my algorithm, level 3 seems to have 15% of the space behind him. That's quite big. So this ranking is quite, I think it's quite good. And the advantage compared to other methods, it's like, it's not a black box. It's something public, and it takes care of the bias. So the overestimation of some things are pushed out, or average, we can say. We take advantage of the multiple vantage points. So the more vantage points we get, the more accurate we will be, maybe. And finally, I can say, instead of computing the IP space percentage, we can use the relative importance of prefixes. We can weight prefixes based on the content to get another rank, to give to give an AS rankings that should take care of the the BGP data and also the data from the content inside a prefix. Okay, thank you very much.
Thank you, Mickael. Any questions?
I would be grateful of feedback about that because so many black boxes exist. And feedback from ISP or people that negotiate agreements will be good.
Okay, thanks. We're ready for the next speaker.
I got one question.
Oh, sorry, question over there.
All right, Roger Kim from Switching Data Packs. I'm sure you've done some kind of analysis, pre-analysis of something like this using this method, and wanted to know what the results were as of preliminary analysis when you did it this doing this current method. Who came up at the top?
Who came up at the top? Yeah, that's your question is who came up at the top? Yes. Yeah. So you mean those top 20 or those others?
Oh, okay, I see.
And when I talked to operational people from France Telecom, they told me they have the impression that level 3 was very high, and I can say it's first.
Randy?
Randy Bush, IJ. You might want to talk to some of the operators around and see if their impression of that ranking approximates their impression of reality. Doesn't match mine.
Doesn't match well, you think? No. Oh.
There are some anomalies there that are hard to believe. Could you go to the next foil? I believe.
Which one you think?
Next.
Oh, sorry.
Hit down. Is that 702 is number 25?
702 was a UUNet, no?
There are just things that...
Okay.
Andy Ogielski, Renesis. There is a reason for this, of course, and the reason is that you are comparing apples and oranges, in short. You cannot meaningfully compare providers who operate in different market segments. There is a different metric for retail providers, there is a different metric for wholesale providers, and say the largest tier ones, including NTT, are providers, we would say. And in each case, a different metric applies to more accurately account for the relative position in the market.
And is this metric applicable to prefixes?
In each case, it's weighted by traffic, meaning by prefixes in this case.
Yes, so with my algorithm, you can put weights on prefixes and get
and secondly,
the rankings you want.
Yeah, and second division is by geographic regions.
Yes.
You cannot meaningfully compare, say, global networks to regional or continental networks. That's the second
Yes,
division by markets.
You can apply other data to this algorithm because it's like a framework to compute things. Because when we take a look at customer prefixes provided by customer cones provided by Kaida, for example, if you get into the data, you will see many erroneous things because I got inside. And for example, in the inferring relationships, you've got cycles of customer-provider relationships. So every AS on the cycle get the same cone. It's just an example. You've got the example of Colt, and I didn't mean your ranking was not good.
No,
I just mean this algorithm was public, and we could all benefit from public things. I mean, so operators can see, okay, this ranking means exactly that. That's the way it is computed. We all know it, and we all know the limitations, for example, but we know it. It's better than to say, okay, I can provide you a ranking, but I cannot tell you because it's too complex how I compute it.
And there are reasons for this. I'll just comment. The number of malformed or otherwise weird updates that cruise the internet is rather large. If you don't have layers upon layers of heuristics to remove effects of leaks, misconfigurations, unintended, the aggregations and such, you can come up with pretty strange results. I don't know whether they impacted your list, but it's just a commentary in general on methodologies.
But I've got something to reply to this. In fact, this is computed using BGP tables, and you're right. In BGP tables, you've got some temporary things inside. But so in my PhD, it's not in English, I'm sorry, but I propose the methods so you can get successive BGP tables, and you analyze those successive tables, and you get the underlying stability from that. And for example, you can also filter temporary announce, backup links, as you can see them as backup. I mean, you can, if you see links only one time over 30 tables, you can say it backup. So you remove every route with these links. So using this, you get, so you can filter the input data and push it in the algorithm. But the real idea of this algorithm is really the framework of computation.
Okay. I just had a general comment.
But thank you for
There is
your...
a lot of heuristics and strange things in the internet.
I really thank you for your questions.
Okay, Bill?
I think a big part of what you're hearing from people in the audience is that this is essentially 2/3 of the same analysis that Renesas does and that we do and so forth. And the same thing that was published in the Cook report in 2001. And the basic issue is that this sort of topological analysis gives you a really good framework, and it's useless without the traffic weighting, right? So the net flow exports that you flow into this in order to get a final ranking as opposed to a topological ranking, which really isn't interesting by itself, right? It doesn't tell you what you want to be doing with your routing policy. Once you flow your traffic into it and re-rank it that way, then it becomes interesting. But it becomes interesting from a specific point of view, your point of view, the person who exported that traffic, right?
You're absolutely right.
And these rankings fluctuate hugely by time of day, right? By which IX you're exporting the net flow stats from, even within your own AS. You know, these things, you see things bopping back and forth between, the top 10 and, the 200 and 300s over the course of a day. So showing any one ranking like this, I've never found to be very useful unless you're looking over a span of, months and over all the routers in an AS. And even then, it's just that AS.
So you mean traffic fluctuations is not our friend to apply with the algorithm? I'm sorry, because my English is not so perfect.
Yeah.
So.
Okay, so what we found back when we were first doing this was that we didn't see the list start to stabilize until we started looking at 20-day windows.
Okay.
Right? So once you got out past a 20-day window of averaging, you'd start to see things stabilize over the course of a day.
I see.
But if you were looking at like a 15-day window, you'd see a huge amount of churn doing the same report over the course of one day.
Okay,
right?
so you're right, the fluctuation of prefixes, you ever get a small fraction of prefixes making the whole, but it fluctuates over time. But I didn't know we have to take at least 20 days or more. So you've got to average the traffic over prefixes to apply to a ranking.
I suspect how big that window is also going to depend a lot on how big the network is that's exporting the data. So, you know, I think there are a huge number of variables here.
Yeah, that should be
interesting
a good
analysis,
study.
but yeah.
Yes, but actually it's better than knowing nothing. Thank you for the question.
Okay, thank you very much, Mickael.
Thank you.